Good evening, everyone. Great. Okay. So today I'm going to talk about how artificial intelligence is sort of changing the game in scientific discovery. Every civilization at some point of time, or once they become sort of sophisticated, they do something remarkable that changes their path. From that point on, what they do is completely different. With fire, we started cooking. We started having nutritious food, which eventually led to the development of brain and intelligence and consciousness and so on and so forth. In a sense, fire is all about automation of nutrition. With wheel, we realized who we are. We are travelers. We are explorers. The very idea that we want to move from one place to another place have a profound impact even today in our lives. In a sense, wheel is all about automation of mobility. With artificial intelligence, we are at the cusp of seeing something remarkable, something revolutionary. Artificial intelligence is not a fiction and not something that for the future. It's here and it is real. In a sense, artificial intelligence is automation of intelligence. From your cell phones to self-driving cars, artificial intelligence is already part of your lives. Artificial intelligence is a very broad sort of ideas and concepts. It's about building systems that can observe, learn, and solve problems. Machine learning is a promising approach to build such systems. Okay, it's a very data-centric approach. It's a set of ideas, algorithms, and concepts that we use to build such type of intelligent systems. Artificial neural network is a class of machine learning methods that is actually revolutionizing the whole field of artificial intelligence. And we will be looking at some of these things in this talk. Before getting into how machine learning or how we build artificial intelligence systems, let's take a step back and see how we solve problems using computers. Okay? So given a problem, let's say take a simple problem, addition of two numbers. So given this problem, what we usually do is we come up with a set of steps, something like this. How to solve the problem. Take two numbers, add it, and print the sum. And then we translate that into set of instructions. So this is like English-like language. This is the computer program. And this is the program, and this is the language that computers understand. Okay? So once we have that program that can solve this problem, we take that program and put it into the computer, and given new data, that will give us the output. Okay? Starting from addition of two numbers all the way to really solving complicated problems, we follow the same approach. We think about the problem, we come up with a set of instructions, how to solve the problem, and translate that into a computer code, and then load it into the computer. Okay? Machine learning, on the other hand, is a completely different approach, where you load the machine learning algorithms into the computer, and you give a lot of data. So in the addition of two numbers example, you give two numbers and the output. Not one, not two, but thousands of them, thousands of examples to the computer. And then machine learning does something remarkable. It will produce a program. Okay? That program, you can then take it and then solve problems. In the case of addition of two numbers, you use those programs to solve those problems. Given new two numbers, it will predict the sum. Okay? So the difference between the machine-generated program and the human-generated is shown here. The human-generated, we can understand, and computer can understand. The machine learning-generated program, the machine understands. Sometimes we understand, and sometimes we don't understand. Okay? Machine learning, talking about machine learning is very close to how we humans learn. Okay? Broadly speaking, there are three different classes of machine learning approaches. Supervised learning is similar to how we learn from our teachers, parents, and mentors. Okay, someone is there to supervise, okay, this is the right thing to do and this is the wrong thing to do. Unsupervised learning is something that how we learn as kids. Before someone come and tell us that this is a chair and this is a table, we know what is a chair, we know what is a table, and we know what is a pen. Of course, someone has to come and tell us that, okay, this is a table and this is a chair, and then we learn to associate the names with the object that we already see. So we already understand a lot about the world that we live in without someone telling us what the world is made up of. So that class of algorithms are called unsupervised learning. Reinforcement learning is something that how we learn every day, even today, right? So we do something and we experiment with something, we get some reward, some feedback, and based on that we change our actions for good or for bad. So that's reinforcement learning. Let's first look into what is supervised learning. What is difficult for a computer to say that this picture is a cat picture rather than a dog picture or elephant picture, or sending a rocket to Mars? How many of you think that predicting or saying this cat picture is difficult? Please raise your hands. Okay. How many of you think sending rocket to Mars is a difficult task? Fantastic, you predicted it right. Computers can do that because we understand the math of sending rocket to Mars, and we can put it into the computer and the computer will take care of it. Okay, in some sense. But still predicting that this picture is a cat picture rather than a dog or an elephant picture or a horse picture, it's a very complicated task for computers. The system that can do this very well is our brain. You predicted it right. So that's a cat picture, right? So this is the brain, and this can do this job so well. And the fundamental unit of brain is so-called neurons. It's a special type of cell, and all it does is receives signals from nearby neurons and fire once it reaches threshold. Taking inspiration from this type of computational unit that is already in our brain, can we build a system? And that's what artificial neural networks are. Okay? So the neurons connected by dendrites receive signals, and once it reaches a threshold, it fires. And with that simple computational approach of the neuron, we see intelligence, we see consciousness. We can do really remarkable things that the computers cannot do. And replicating that with the computers is this approach called artificial neural networks. And this idea is not new. This existed from 1952. Okay? So let's go back and see how we can say that this cat with this artificial neural network can say that this is a cat. Okay? So the supervised learning approach is one in which you have a set of inputs where the inputs are the cat, dog, horse, elephant, and you explicitly tell this is a cat, this is a dog, and this is a horse. The very fact that you tell this is a cat and this is a dog and this is a horse, that makes this approach supervised learning. Because we, or a human, has to supervise the machine saying that here is the input and here is the output. Okay? And then the neural network undergoes a process called training. And that results in a model or a computer-generated program. With that program, then given a new image, you can predict what this image is. So what is the secrecy behind the training? So that is the sort of the secret sauce behind neural networks, right? So what is really happening? So for that, I want to tell you a story about my grandmother's soup. My grandmother makes really good tomato soup. It's so good that I can always tell that is my grandmother's soup. And I can differentiate that soup from any other soup. Okay? So one day I wanted to make that soup. I know the ingredients. Okay, it's made of tomatoes, salt, pepper, and water, but I don't know exactly how many or how much I have to put for the soup. So I start with some random quantities, and I make the soup. And then once I make the soup, then I taste that, and then I know, oh, this soup has more salt than my grandma's soup. And then I try next time and then say, oh, this soup has more pepper than my grandma's soup. So I slowly started changing my the amount that I put in terms of salt, pepper, water, and tomato, and eventually I made a soup, which is similar to my grandma's soup. Although my grandma doesn't agree, but I made it. Okay. So what is happening? So based on the feedback that I have about my grandma's soup, I'm slowly changing these knobs. Think of these knobs as sort of the way to control your tomato, salt, pepper. Okay? This is what's happening with the neural networks as well. In the beginning, we start with neural network, we give an image, and we ask the neural network to predict what is the output. And it will predict randomly, instead of predicting its cat, it will predict a horse. But the fact that we know a cat image is a cat image, right? That's where the supervised learning is all about. And then once we know those differences, then we go and tune the knobs in such a way that it can predict cat as a cat. You don't do this once, not with one image, but you do this thousands of times with thousands of knobs. Okay? To make it more powerful, what you can do is to increase the size of the neural network with millions of knobs. Okay? So we don't do this random way of changing the knobs to make the prediction better. Instead, there is some math. And believe me, this is really a high school math. Okay? That's what allows us to go and sort of correctly identify what knobs I need to sort of fine tune to make this prediction better. Okay. So what you see here is one of the state-of-the-art type neural network. You see many layers, and this is how the neural network for vision, so given a human face, it can say who this face belongs to. And those type of applications you already know. You upload your Facebook, you upload a picture in your Facebook, and it automatically says that, okay, this person is this, and this person is this, right? So that sort of application. Okay, so what is interesting, what is happening, and what is really the neural network learning here? So at the lower part of the neural network, once after training, we can go and inspect what this neural network is actually doing. And what you see here is at the lower part of the network, you see the sort of edges. And you go a little bit upper part of the network, you see textures. And the textures were put together as patterns, and patterns were put together as parts, and finally objects. You know the cool thing about this? It's very similar to how we humans recognize objects. And you know what is a game-changing thing about this? We didn't explicitly program anything. We just give examples, and the neural network managed to do this. Okay? Such type of supervised learning is fundamentally changing many different applications, not only in the commercial world, but also in the science world. So if you look at the commercial world, recognizing the faces, speech recognition in your phone. You say something, your phone recognizes that and performs some actions. Shopping, Amazon, autonomous driving, and all the way up to healthcare and finance. So there are numerous applications because we are spending a lot more time online and generating a lot of data, and these data are the new gold. And these data were used to train these type of models. Okay, why now? First thing, as I said, a lot of data. And the second thing, to crunch this data, to train a neural network, you need a lot of computing power. And now we are having this cheap but massive computing power that no other civilizations had on the planet Earth. And even our civilization, up until 20th century, they didn't have access to this much of computing power. But we have it. We have both data and the computing power to do this type of learning. Coming back to science, how these type of approaches are sort of changing the phases of scientific discovery and scientific development. So think about just Argonne as a science lab. We have 5 world-class user facilities. People here at Argonne and people from elsewhere come to Argonne and do experiments, starting from big supercomputers where we generate, where we simulate from atomic level all the way up to cosmology, galaxy, and universe type simulations. And advanced photon source, this very building generates tons and tons of data. Okay? So there are many different facilities, and also coming from more application perspective, there are many different applications that produce a lot of data. And all of them require way to process the data, way to build predictive models. So we will look at some examples how supervised learning is used in different areas of scientific applications. So the first one is accelerating high energy physics, where, so this is an experimental facility in CERN, Switzerland, and you can see how big is this facility, just one part of it, and you can see the human scale in that big experimental facility. So what people are doing here is take two particles and accelerate really fast and make them collide so that we can go and understand what matter is made up of. Okay? So this is not about atoms. This is about, so the atoms consist of nucleus, which is much smaller than the atom itself, and people want to understand what is inside that atom. Okay? So if you collide these two particles, then what happens is, whatever inside the nucleus comes out, and what you see as a pattern on the other figure, the different yellow lines, that shows how these particles behave when they collide. And people have theory about it, and when they do this experiment, they want to take these images and analyze them as fast as possible. People were doing these kind of things previously, but these are all hand-coded programs. It takes a lot of time, and they are not robust because once you upgrade these facilities, things become difficult. You have to reprogram or come up with a new way to analyze this data. But now, with supervised learning, what we are doing is we just take the particle trajectories and tag them and create a lot of supervised examples, input, output, and let the machine learning learn to associate the particle trajectories with what type of particle it is. Okay. So simulation, going back to supercomputing and simulation. So simulation is such a sort of central theme here at Argonne. We simulate subatomic particles all the way up to cosmology. And most of the time, simulations are very, very expensive. And people were using these big supercomputers to do simulation. How machine learning is changing the game is as follows. Instead of generating lots and lots of simulations, we can generate a subset of simulation, learn from that simulation, and predict the rest. An example is shown here where we were trying to do vehicle simulation with a different set of inputs. So this is assessing the different type of vehicle technology, starting from vehicle class, vehicle powertrain, and so on and so forth. There are 28 different inputs, and then the outputs are going from engine max power all the way up to how the battery total energy consumes for this type of configurations. So here, we are not building the vehicle, we are simulating the vehicle. And each simulation is expensive, but then we can generate, let's say, 3,000 simulations and predict a million different configurations in less than a second. This type of capability was not there before, and machine learning is allowing us to do that type of prediction in sub-second, and we can study a lot more different simulations, a lot more different vehicle configurations, and understand what type of vehicle configurations are better. In another project, we are looking at mobility design and planning. So traffic is a problem probably everyone in this audience have encountered, right? So we are using machine learning to sort of understand how to address the problem of traffic. So here, the supervised learning approach is take the historical data, like 1 hour of data, and the next 1 hour as the output, and we let the machine learning to learn the input-output relationships. And given a new 1 hour data, we will be able to predict what will happen for the next 1 hour. What is interesting here is we can try to predict using these models as soon as an incident happens, let's say an accident happens, we know how we can use this model to understand how the traffic dynamics is going to affect and how the traffic congestion is going to occur. And using those type of proactive approaches, then we can do mobility planning, how to reroute the vehicles in different roads so that you don't have this 3-mile, 4-mile traffic jams. And we also want to understand how these things affect energy consumptions. So one way to do this is simulations, but simulations are expensive. We can also use simulations, but we can use machine learning on top of it, learn from the data, and then do these kind of studies. This is another project that we did with the city of Chicago, where we were trying to predict on a given day which restaurants are going to violate sanitary conditions. Okay? City of Chicago has several inspections, rodent inspection, elevator inspection, and so on and so forth. And these inspectors are integral part of the city because they make sure that the city functions in the way that we want, right? And they don't have a lot of resources. And on a given day, what they do is randomly go and visit some restaurants and see whether they violate sanitary conditions. And what we did is we took the data, historical data, and sort of characterized what type of restaurants, and then we correlated that with 311 calls, rodent compliance, and so on and so forth. And then on a particular day, based on the restaurant characteristics and based on whatever the complaints that were received near that area, we will be able to predict what type of sanitary violations that this restaurant is going to make. And based on that, we can send those limited number of inspectors to go and inspect those restaurants first. And what we did as a simulation study is machine learning can really help to do those predictions, and we can predict sanitary condition violations at least 1 week in advance, just for three months of time. So this is another example how machine learning can help for very unusual type of data. Okay, so let's look at what unsupervised learning is all about next. So now it is possible to take a bunch of images and let neural network train with those images, and then we can generate images from those neural network. Okay. An example that you see here is the images that were generated from those neural network, and what you see here is a smiling woman minus neutral woman, so we can generate those images, group them, and then do arithmetic operations on those images, asking the neural net, smiling woman minus neutral woman plus neutral man, what is the output? And the neural network will say, it's a smiling man. What is the big deal about this, right? The big deal is follows. We do this kind of abstract calculations on abstract concepts so easily. It's a sort of a proxy for intelligence. Now, neural networks can also do that. I think that is game-changing. So here is another example where the neural network was trained with celebrity images, and then it generated a new set of celebrity images. Okay. How many of you think 2 images in this 8 set is generated by computer, by neural net? Okay. How many of you think that 4 images? How many of you think 8 images? Okay, 8 is max. So yes, all those images are generated by computers, by neural networks. Why this is a big deal? Because we didn't explicitly program how celebrities look like. We just took a bunch of images and let the neural network learn from those examples. And then it generated this kind of realistically looking celebrity images. For science, let's say if we can generate those kind of data with molecular structure, it's a big deal because we don't need to go and generate those molecules, but instead of that, we found a way to teach neural networks how molecular structure look like, how bonds look like, how carbon atom look like, and so on and so forth. Okay. The way that people do this is using this approach called a detective and forger. So the story is this. Okay. Let's say there is a detective, and he can detect whether a painting is a fake painting or it's a real painting. And he does it so well. And here comes a forger who has access to how this detector meticulously looks at these images and try to find which image is a real image and which is a forgery image. Once a forger knows how the detector is detecting, then he can make really good, realistic looking images. Okay? The idea is same. What we do here, we have a detective neural network for which we give a fake image and a real image. Once, this is a simple supervised learning, right? So fake image, real image, and ask the detector to, we train the detector to differentiate between the real image and the fake image, right? And then you give access to the forger neural network, right? Once the forger neural network know how this detective neural network is differentiating these two, the forger neural network will know how to forge, how to better forge in such a way that the images produced by the forger neural network is undetectable by the detective neural network. What we do with those type of approaches is, take for example this advanced photon source facility, right? Here we generate a lot of data, and that data need to be moved to supercomputing facilities for analysis. And the amount of data is so huge that if you try to transfer it directly, it takes a lot of time. Okay? So what we do here is to have this forger and the detective type neural network. So we compress in the image into really sort of a small image that is easy for transfer. Okay? And then we train the detective neural network in such a way that the detective neural network knows how to differentiate the uncompressed image and the compressed image. Then we give access to the forger network. Then the forger network, given a new compressed image, it will learn how to forge it in such a way that the detector cannot detect. Consequently, what happens is you get the uncompressed image without any artifacts. What is game-changing here? We can do this on thousands of images within a second. This allows scientists to move large amount of data from one place to another place and do the analysis in a much faster way, otherwise not possible. Okay. Reinforcement learning. So reinforcement learning, as I said in the previous part of the talk, it's about how we learn from the real world. We perform actions. For those actions, we get rewards, and based on the reward, we change our actions. Okay? So the reinforcement learning framework is very similar to that. An agent performs an action in an environment, gets a reward, and based on that reward, it changes its actions. Simple framework, but very powerful. You all know this game, right? The paddle game, where you have to move the paddle up and down and make the ball move to the opponent. And if you lose the ball, then you lose. Whereas if your opponent lose, then he loses the point and you gain the point. Okay? Let's say if you want to build a system, if you want to build an AI system that can play this game, how to do that? The simple way is to take the supervised learning approach, right? We can take all those images, right? So let's say you hire me and I play the game and you see, okay, for this particular image, I'm moving up. For this particular image, I'm moving down. And I can generate thousands of those images and then simply apply supervised learning. Inputs, outputs, neural network training, and it produces a model, and then given a new image when you are playing the game, then you can say whether to move up or down, right? What is the problem with this approach? First thing, for the simple game, we need to generate thousands and thousands of examples. And the second problem is if you hire a mediocre player like me, the system is going to be as good as me, right? But what we want to design is a system that can outperform me. And that's where the reinforcement learning comes in. The reinforcement learning formulation is shown here, where you let the neural network play the game. In the beginning, neural network will make random actions. Sometimes it will win, sometimes it will lose. Whenever it wins, go and tune the knobs in such a way that those actions are favored. Whenever it loses, go and tune the knob so that it cannot perform the same set of actions again. And then you repeat this thousands of times, and eventually the neural network gets better in playing this game. Google used a similar approach to play the game of Go. And what happened is the AlphaGo, the system is called AlphaGo, and it becomes so good that it beat the world champion 4-1. Okay? For example, to give you more information on this, Go is billion times more complicated than the game of chess. And before this game of Go, computers, if you're an average player in a game of Go, you can easily beat the computer. But now, this AlphaGo can beat the world champion 4-1. And then they built other systems that can beat this AlphaGo 1000-0. That's a different part of the story. Okay, so game of Go, fixed board, moving things here and there. Okay, it's a limited edition space. How about the strategy game like StarCraft? Okay, so what happened here is, again, they followed a similar type of approach, and they managed to beat the world champion 5-0. Okay, we don't play games here. What we do is we use similar type of approach to design neural networks. Okay, why? Because designing neural network is a complex task. Even right now, how we approach this problem is we humans, experts, design the neural network given a problem and try to experiment with them and make it better and better and better iteratively. Okay, the neural network that is shown here, it's a simple neural network, and for each of the white box that you see, you have to make a decision. And if you put just 10 decisions, 10 decisions for each of the box, the number of possible neural network configurations that you need to explore is 10 billion. And it's impossible to explore all of them in reasonable amount of time, even with supercomputers. Okay, so what we do, we use reinforcement learning to automatically design neural networks. The agent here makes some decisions, as shown here. It makes sequence of decisions. This cartoon illustrates that sequence of decisions here. Once it finishes this, we will go and evaluate that, or the agent will evaluate that, find the accuracy. Sometimes it builds good neural networks, sometimes it builds bad neural networks. Think of the paddle game. Whenever you do good, go and sort of reward yourself, or the agent will reward itself to build a similar type of networks. And slowly it improves, and slowly it can build a very good neural network. With that simple approach, it can build really complex neural network. Okay? So we applied this to the problem of cancer drug discovery. Okay, so one of the key problems in cancer drug discovery is, given drugs and tumor, we want to understand how this drug interacts with the tumor. Is it a good drug or a bad drug? And the supervised learning approach for this problem is you take a bunch of drugs and how these drugs interacted with the tumor in the past, and now you have a sort of a database for that. And now you want to build a neural network that, given a new drug, you want to predict whether it's a good drug or a bad drug on this particular tumor. Okay? So this is the results of automatically generated neural network using reinforcement learning. Okay? So at one, which is shown in yellow, that's a manually generated neural network that took months to design. In this plot, higher the better. Okay? All the red dots are different neural networks, are the best neural networks that were found by reinforcement learning. Okay? On the y-axis, you see the accuracy, which means the red points, all red points which are above that yellow, actually outperform the manually generated one. Okay? And this is not about coming up with one single model, but with multiple neural networks that have better accuracy than manually generated one. And do you know how much time it took to generate all those models? 6 hours. Okay? So generating multiple models, there are gives several advantages. The first one is technical, right? So we asked this survey, about the cat versus sending rocket to Mars, and several people, or most of them, said that identifying cat is a difficult problem, right? It's a similar thing. When you have several different neural networks, you can do prediction with several different neural networks, and all of them agree on the result, then most likely that's going to be a good result. Okay? And the second one is more philosophical. Okay? Intelligence is not just inside our brains. Intelligence is here. Intelligence is a collection of brains. Intelligence is outside our brain. It's the civilization, it's the culture, it's the language that we have. That gives us a lot more intelligence than a single brain alone. Okay. With that, I'm almost coming to the conclusion of my talk. If intelligence is a cake, okay, supervised learning that we are doing now, a lot of supervised learning, It's really good, but it's icing of the cake. But what real intelligence is all about is unsupervised learning and reinforcement learning. Imagine if we can build a system without human supervision that can learn about the world, that can learn about the physics, that can learn about the chemistry. How cool that would be. So that's why unsupervised learning and reinforcement learning sort of the central aspect for intelligence. I want to end the talk with this one interesting study where they took this game, like the Atari game, and they let the human play this game and reinforcement learning agent play the game. The first, the first square box, there you see original game. So that's the original game where both of these guys played, and humans outperformed reinforcement learning agent by far, both in learning time and also in the score. Okay. Then what they did is they started tinkering with the game dynamics, tinkering with the physics of the game, all the way up to, they started the gravity. Instead of gravity, if you jump like this, coming down, if you jump, you will go on the sideways. Okay? So what happened there is the AI agent, or the reinforcement learning agent, took the same time that it took for the original game to learn the game and to play very well. On the other hand, humans failed. They failed miserably. Okay? So what this means for science, when it comes for artificial intelligence and machine learning, is that go and ask any scientist in this lab. They will admit that what they know about their field and what has been discovered in their field is just a drop. And there is an ocean to explore. And I truly believe that machine learning and AI are going to help us to explore that ocean, to navigate that ocean, and to swim that ocean. I can't wait to see artificial intelligence helping us to find a battery material that can charge in 2 minutes and can get us 400 miles. I can't wait to see artificial intelligence helping us to uncover the mysteries of the universe. I can't wait to see artificial intelligence helping us to find a new drug for cancer. With that, none of this work is possible without the brains shown here. And I would like to thank my collaborators. And it's not just the people who are shown here, but collaborators outside Argonne, within Argonne, who are not shown here. And I would like to acknowledge the funding agencies which allows us to do this type of cutting-edge research. And finally, I want to thank you.
Thanks, Prasanna. That was awesome and kind of fun. And games. We love to play games. We like to build programs that play games to teach us about the world. So we have some time for questions, and we like questions. And so we have some ushers with mics, and there's a person down here who I think was the first to hand, and that's the second person there. So this one, and then back there, and then I'll try to track. So ask your question, and we'll
Hi, my GPS is occasionally, like maybe 1 out of 10 times, leads me to the wrong place. So I'm just wondering how you account for that kind of thing.
So there are many different reasons why the GPS didn't work, right? So there is a sensor problem or identifying the localization problem, right? Where you are in the map, that matters a lot. And the other thing is you have to make that mistake a lot of times so that the machine learns, and you have to give the feedback to the mapping application saying that this has given me a bad route, and that allows the model to learn that it is making bad decisions and help to sort of improve over time. That facility doesn't have that doesn't exist in the phones or in the GPS now, because the models were trained somewhere and then they were sort of given to your phone. But soon, you should be able to give those sort of feedback and able to correct your locations.
Here.
Electrons or photons?
Sorry?
Electrons or photons?
In what sense?
What are the new chips going to be?
Sorry, I didn't understand the question.
What will the new chips be?
The new chips.
What are the new chips? That's a very interesting question. So because of AI, there's a lot of interesting things happening in the chip space. Designing new chips that can do learning on the edge, on the big computing facilities, and so on and so forth, all the way up to thinking about replicating the brains using neuromorphic computing, neuromorphic chips. So we are in a very interesting time when it comes for chip design. There are many different possibilities, and we have to see how this is going to pan out.
In the short term, my money's on electrons still.
Yeah.
Next question. Lots of questions. Over there. Wait till you have a mic, then you can ask it, and everybody can hear.
I saw the slide about the compressing the video image, and I can see that is being very instrumental in future communications. We're up to 4K, and there's 8K televisions now for people who have gone and seen these at the shows. And I can see there's a tremendous amount of things that need to be compressed and then decompressed, and that's really an interesting thing of doing without the artifacts, and that's going to be the future. It's really going to be something.
Yeah. So I'm not an expert in the 4K television field, but when it comes for science, we are very excited about those type of opportunities, and we want to do this type of compressing at the edge where the experimental data were produced, and then transfer it to facilities where we can do those type of analysis and things like that. So the possibilities with these type of approaches are sort of endless. What is key driver there? We can, once we train, training is still a sort of a bottleneck, but once we train this is really, really fast. We can send million images and do that in less than a minute, decompress them. So I think that sort of opportunity, I think when it comes for transferring, let's say, a movie in a compressed format and decompressing that with the television, it's potentially an interesting idea.
Okay, we need a mic kind of right there. Yeah, there.
What's the role of quantum computing
You guys aren't
in
following
the future of
directions.
machine learning?
Go ahead.
The role of quantum computing, machine learning?
Yeah.
So we are still exploring what quantum computing can do for machine learning and what machine learning can do for quantum computing. So one of the biggest challenges that we see with respect to quantum computing is the data. So if you think about machine learning is all data centric. We have to put a lot of data into a quantum computer to do the quantum computation. If you see the training, so training is essentially an optimization problem that can be better solved if formulated correctly with the quantum computer much more efficiently. But the problem is how to move this data, how to take this data and put it in a format that can be represented within the quantum computer. So it's still an open question, and here at Argonne, we are also looking at quantum computing as one of the key driver for sort of future computing, and yeah. So right now, it's an open question. It's an open research question.
Okay. Over here, the person.
Over here. Hi.
He's been waiting, so bring the microphone right there. The one who raised your hand. Keep your hand up so we can find you.
Yeah.
Grab the microphone and give it to him. All right. Now, ushers, pay attention to our point two. That's who gets priority. There you go.
Yeah, thank you for the talk. Okay, I think right now the machine learning is very powerful in the pattern recognition and the languages. Okay, and the reason we give it the name the machine learning because the architecture for this neural network mimics the human biological neural network, right? But I think the learning, in sense of learning, is still very different because the human learning doesn't need to crunch through a big data, a huge amount of data, then we can learn that, right? So therefore, how to making the machine learning more closer to human intelligence?
Okay.
That's one thing. And the second question is, well, in order to achieving the goal you saying at the end, so we can using the machine learning to discover something new, that kind of thing. I think that's one missing steps. Okay, for example, human being can infer the causal relationship, but if you open up the neural network, it's just a black box, right? It's just, for example, the supervised learning actually is just from the statistical point of view, just the data fitting. That's it.
Yeah.
Nothing more, right? Okay, but so therefore, in order to reaching that, you have to go closer to human intelligence. For example, you can infer the causal relationship. So therefore, then what's the present status for the machine learning on the causal inference?
Yeah.
That's the second question.
Okay. Very, very interesting question. So let's not forget our brain evolved over millions of years. Okay. So a lot of intelligence that we have, it's already evolved in our sort of encoded in our brain one way or the other. So we are not learning from scratch. The very fact that we have a brain and this is of this structure, this is evolved. This is evolved to perfectly fit for the world that we live in. Whereas the neural networks, I agree, it's data hungry now. We are just getting started. It requires thousands of cats and thousands of dog images to say what is a cat and what is a dog. Whereas we humans do that with let's say 5 images. Or we see a dog and we can generalize a dog even if you haven't seen that particular breed of the dog. But those things comes from the fact that we know a lot about the world that we live in, even before we start learning. So a lot of this unsupervised learning and the very fact that we can recognize objects and our brain can recognize those objects and put it in a form that can be sort of matched into a pattern, that has been evolved over millions of years. And we are just getting started with respect to neural networks. So there are new developments in terms of causal relationships and so on and so forth. So there are a lot of interesting developments in terms of machine learning and AI, and that's what I'm super excited about. And those things will, moving forward, will bring down the very nature of the data hungriness or how much power we need to learn and so on and so forth. So yeah, I agree. There is the way that we learn now is not the way that our brain learns, not one-to-one, but we are slowly moving.
So the little guy to my left here would like to know whether artificial intelligence could potentially be a danger to him in the future.
Asking for a friend.
So artificial intelligence is like any other technology. It has its own advantages, and it can be used to do harmful things as well. So I have to admit that. For one of the biggest concerns that people talk about is job loss. I'm not talking about your future, but I'm talking about what's happening now, or what sort of challenges that people see. I mean, we had telephone operators. We have elevator operators. What happened to those jobs? Right? So artificial intelligence will automate several things. But at the same time, I'm also excited about artificial intelligence for education. AI looking at this person and see what type of skills that this person can learn so fast, so that he can learn this particular subject very well and be ready for the job market. So my answer to that question is AI is like any other technology. It has its advantages and disadvantages. So I don't think it's too early to sort of see that this is a danger. Are you happy? Great.
Right there, over there, to the right.
Is Argonne considering a partnership? Is Argonne considering a partnership with OpenAI to analyze the data collected?
Argonne is with is
I
a
think the
partner
question
with
is, are we
company.
considering a partnership with OpenAI? Is that the question?
Yeah.
Yeah.
No, we don't have direct partnership with them, but the nice thing that is happening with the AI research is a lot of these things are open source, and we learn from each other. It's not about, okay, who built this first, but rather than, okay, what you guys did and how I can take that and make it better, or how I can take this and solve problems in science. So in that way, we are not in a position to have a strong sort of formal relationship with OpenAI, but a lot of work that OpenAI is doing now. It's we take them and then we see how to make it better, how to scale them on our big supercomputers, and how to use that for solving science problems rather than playing games.
Okay, over here.
Can you describe an example where the machine learning sets its own goal and the quality of achievement of that goal?
Okay. So a lot of this unsupervised learning falls into setting own goal, although it's we humans who are taking this centerpiece and saying that what the machine want to learn, we sort of architect that, and we call that as sort of reward shaping in reinforcement learning, and in unsupervised learning, we specifically design what is the objective of the learning. Right now, it is not that you let an agent just do whatever it wants and achieves the goal. So there are some recent work in terms of in the context of games where you let the agent to sort of explore an environment and see how curiosity helps. And so a lot of this also has sort of inspiration from how we look at things. We are curious living beings, and we go and explore things, and people were trying to imitate that in the context of game. But most of the work that I presented here doesn't explicitly have complete autonomy where the agent goes and tries to find things.
I could point out there is a type of learning called active learning where the system gets to choose the next data to label or the experiments. And in that case, it's prioritizing things that would ideally improve its accuracy. So there is that concept called active learning. We have time maybe for one or two more questions. We've already got a mic over here, and then get a mic over to that guy over there. Yeah.
Hi, so the question was like, there's a lot of data collected, right, already, and a lot of data would be also collected by, for example, Watson have a lot of data, right? So does the IBM share that knowledge to the open AI, which is there like an international open AI like a body which governs the data or something which would be helpful for the human mankind, right? Like whatever, because it takes a lot of time to aggregate the data and to make something meaningful out of that. So is there something technology or something which is shareable?
Okay, so just from the data perspective, right, there are two different things. One, there are curated data for research purposes that people develop algorithms and compare, and that helps us to improve the state of the art so that we know that on a common set of data, we are comparing different methods and assess the effectiveness. But on the other hand, think about Watson. IBM wants to make millions of dollars with it. Google will not just expose their data to us because it's not the algorithms. It's not, they are giving us the algorithms, but not the data. Okay, so in that sense, we share a lot of models, a lot of neural networks, a lot of ideas about how to build models, how the model works, and so on and so forth. There are a set of data for doing experimental research, but when it comes for data that allows you to make millions and billions of dollars, good luck.
Okay, maybe one more question over here.
Where do you see artificial intelligence addressing cybersecurity, weather forecasting, and climate change?
A lot. So to answer about the weather simulation, so we use artificial intelligence to speed up climate simulations. So right now, climate simulations are expensive. If you want to run one simulation, it takes several months on a big supercomputer. What we can do is to sort of mimic these simulations. So you generate a set of simulations, learn from the data, and then predict. Instead of running the simulation, you predict. And this prediction can happen many ways. You can look at the code, or look at the simulation, and see the most computationally expensive part, and then use machine learning to speed up that. Or you can do something like what I have presented here, vehicle simulations. Instead of running simulations, you associate the input to the output, create a set of training data, and then let the neural network learn input to the output. With that, we can now run millions of simulations within minutes, right? So because this is all about prediction. We have to build the right model for the whole simulation, which is a whole different topic. But we can speed up a lot the entire simulation using neural networks or machine learning. And if we can manage to do that, then we can simulate different possible scenarios and then see what type of uncertainty that we are facing, and those kind of things help us to sort of really assess the impact of climate risks going further. To answer about the cybersecurity, yes, there is a lot of work in that area, how to analyze the logs, not just the computer cybersecurity, but also when imagine there are a lot of self-driving cars going on the road, and it's easy to attack those cars and from a cybersecurity perspective and make accidents, right? So there is also a lot of efforts going in that direction. So yeah, there are a lot of potential in both climate simulations and in, generally speaking, cybersecurity.
Okay, thank you. I want to get people out on time. If you want to stick around, I'm sure Prasanna would be happy to answer a couple of questions after you guys break. So. Right. I hope you enjoyed this. I hope it helped you understand a bit better what AI is and how it might impact our science and the kind of work we do here. On your way out, if you can, I think there's some feedback cards maybe for how you thought about today's session went and maybe suggestions for future Argonne Out Loud. So thank you for coming, and thank you, Prasanna.
Thank you.